Welcome to Lesson 3A, Analytical Solutions of First-Order ODEs.
We're going to take a little different path here and look at some math. We're going to look at first-order ordinary differential equations. I'm going to show you how to solve them and do some example problems. Why? Because we're going to see these first-order ordinary differential equations many times in this course when we get into room ventilation, tunnel ventilation, and the next topic coming up is mass body burden, and we'll need it for that. This actually is covered in the first chapter of the textbook. So if you want to read more, see chapter 1 or my ME 345 notes. There's a module of notes on first order and second order systems. So these are same as first order dynamic systems. This should be all review, but I'll go through it in case some of you either forgot or haven't had this yet. We'll just look at some variable y as a function of time, and what we're going to call the standard form for a first order ODE. First of all, ordinary differential equation means it's not a partial differential equation, so y is a function only of time, not of, say, time in x, y, and z. That would be a partial differential equation. The standard form that we're going to deal with is dy dt equal b minus ay. So anytime you're solving a first order ODE, ordinary differential equation, the first thing you want to do is get it into this form, and then we'll be able to solve it. We'll be doing that for a lot of different cases, as I mentioned here in my introduction. So once we have it in that form, we also will need to know y of 0, which is the initial condition, and that would be y at time t equals 0. In general, if a and b are constants, then you can solve analytically. In other words, we can get an equation. I'll show you that equation. If a and b are not constant, in other words, they're functions of time, some special cases you can do analytically, but you typically need a computer, and I'll show you how to do that also to solve these numerically. So we call that a numerical solution. In ME 345, we look at different cases like a ramp. At t equals 0, you suddenly have a ramp or you have an oscillating system. But we're going to look only at a sudden change at t equals 0. So that's the case that we're going to look at. In fact, for pretty much the whole course, we're going to look at cases like that. And let's consider first constant a and b. And I'm not going to go through the solutions for you, but in ME 345 notes, I do that, and you could find these in some of your old math notes, I'm sure, as well. The steady state solution, we'll abbreviate that SS for this case. And so let me just sketch what's going to happen here. Here's time, here's y. We start at some y of 0. And what happens is when you say you're suddenly going along and then you change some conditions so that y goes like a first order behavior, what will happen is it'll asymptote to what we'll call YSS or steady state value. So that's what it's going to look like. And if you think about it, when you look at our standard form up here, dy dt, once it reaches this steady state value, dy dt goes to 0. There's no more change in y. It becomes a constant. So equation 1 becomes 0 on the left-hand side equal b minus a y, and that value of y is this steady state value. So we can easily solve for YSS equal B over A. So once you have it in this form of equation 1, you know what the steady state value is. So that'll be very convenient for us when we do tunnel ventilation and room ventilation and things like that. We have the standard form here, and if you have a step change in constant a and b, you get this solution here in terms of YSS and the initial y of 0, and a, actually b drops out there, but b is necessary to calculate YSS. There's a time constant, tau, that's 1 over a, and there's also a half-life. We'll discuss that in a minute, t1/2. And then here's the expression for YSS that I just gave you. An alternate form of this equation. These are equivalent. It's just sometimes this is more convenient to deal with. Let's talk about these time constants. First of all, mathematicians like to use tau, which is the first order time constant. And as I mentioned, this is equal to 1 over a. So what is it? It's the time for y to grow or decay. I can always say or decay because this works both ways, to 63.2% of its final change, not its final value, but its final change. So the change, if y of 0 is 0, then it would be the final value, but it's the difference between the final value YSS and the initial value y of 0, so it's final change. And that 63.2% comes from 1 minus e to the minus 1. If you plug that in your calculator, you get 0.632. There's a bunch of other digits, but we'll just round it to that. So what we mean is this, mathematically or graphically, if I plot y as a function of time, and again, let's look at some y of 0, and it grows like this to some steady state value, and look at the change from beginning to end, and take 63.2, which would be about that much. So at that point, we'd call this the 63.2% change. If the total change was 100%, that would be 63.2. And where y reaches that value is what we call tau. So time t equal tau, we get to that point. Well, you can plug into the equation also, and you'll find that at t equal tau equal 1 over a, you get that y minus y0 equals 0.632 times yss minus y0. So that comes from either this equation or this equation. So that kind of verifies it. It's 0.632 or 63.2% of the change, the final change from 0 to the steady state value. That's nice, and mathematicians like it. Most engineers prefer the half-life, t1/2, and this is a little bit easier to think about. So it's the time required for y to grow, and I'll specifically say here, or decay, because again, this can go either way. Radiation people use half-life, for example, for the decay of radiation. So you're going from a higher concentration of an isotope to a lower concentration, and there's half-lives associated with that, like carbon-14 versus carbon-12. So you've all heard about that too. So it goes growing or decaying. So it's time for y to grow or decay from now, wherever you're at on the plot, to half. There's no 63.2%, to half of its final change. All right, so let's illustrate that graphically in a similar way. Time, y versus time. And let's again start with some y0, and this asymptotes to some yss. So we start at t equals 0, and we take the halfway point like I did before with 63.2%. Now this is 50%. So 50% of the total change, and we would call that t1/2. That's the half-life. Now we can start there and go another 50%. Now it's 50% of the final change from now. So if now is here, 50% would be 50% of that distance instead of 50% of that distance. So from here, if we go across, that would be another half-life. So that would be 2t1/2. If you do it again, you take 50% of that distance, which would be there, and you come across and you get 3t1/2.
Sir, does that work if you start any place on the curve? Yes, John.
This works no matter where you're at on the curve. If I start at some arbitrary location like here, and then I say, okay, I go halfway between there, and so I come across, and that distance should also be a half-life. So this half-life works no matter where you start. Mathematically, it turns out that t1/2 is equal to minus log of 1/2 over that coefficient a, which was 1 over tau. So this is equal to minus log of 1/2 times tau, or approximately 0.693 times tau is the half-life. They're both times, and they're related. So t1/2 is a little bit smaller than tau, because it takes longer to get to 63.2% than it takes to get to 50%. So that makes sense. If you compare these two plots, you can see that tau is greater than t1/2, although I didn't draw these perfectly scale. All right, let's do an example problem. Here's a first-order differential equation. There's no units here. I'm not worried about units in this problem. So this is just like a math problem. If you have units, you have to be careful that you're doing everything in seconds or in hours. And the y units tend to work themselves out. They can be anything, any units you want, as long as you're consistent. So let's just make up an equation. dy dt is 10 minus 3.82y. And at 0, it's 7.60. This is the initial condition. Let's calculate the steady state value as t goes to infinity. I want this in the form dy dt equals b minus ay, and it's already in standard form if you look at that equation. So we can write a equal 3.82 and b equal 10.0. And so when this is steady, as I said before, this goes to 0 at steady state. And so y steady state is b over a, or 10.0 over 3.82, or 2.618. So I would give this, since everything else is in 3 digits, I would write this as y steady state is 2.62. Calculate the half-life. T 1/2 is minus log 1/2 over A from the equation I gave you, and that turns out to be 0.1814. So again, to 3 digits, T 1/2 is 0.181. Now let's calculate y at the time of 0.54 seconds or minutes, whatever this is. So we'll use this equation that I gave before and just solve. So y0 was given as 7.60 plus y steady state, we just calculated up here as 2.6. I'm going to use more digits than my port because I don't want to have round off errors. So typically I use at least one more digit in my calculations. Minus y0 times 1 minus e to the negative a, negative 0.382 times t is 0.54. And when you plug that in, you get 3.25. So y at t equals 0.54 equals 3.25 be my final answer. Notice that this is smaller than the initial value. So this is a case where we're going down. We're decreasing instead of increasing. So if I sketch this, this would be y of 0 is up here at 7.60 and YSS is 2.62. That's down there. And it would look something like this. And then when t is 0.54, this value would be 3.25 from our calculation. This is all valid for A and B equal constant. We have this analytical solution. If A and or B is not constant, we typically solve numerically.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos.